All right, let's jump right in. Welcome, colleagues, to today's Explainer. Today, we're digging deep into a massive architectural shift happening right now in our industry, the transition from web-based AI to the extreme high-reliability demands of physical AI. Drawing from the comprehensive Intelligent World 2035 report, we're going to unpack exactly what it takes to actually engineer this next generation of intelligence.
Here is our roadmap for today. We'll be moving beyond statistical models, bridging data and reality, looking at next-gen sensors, transforming factories and grids, tackling global safety standards, and finally, designing for a symbiotic tech future. So here's the fundamental systems engineering problem we're all facing, right? How on earth do we cross the chasm between a piece of software that, say, drafts a catchy email and an intelligence that we'd actually trust to operate a national power grid? It is a staggering leap in reliability, and it demands a complete rewrite of our foundational architecture. That brings us to Section 1, Beyond Statistical AI Models. To figure out where we're going, we really have to acknowledge where our current models fall short. Look, we all know large models are having an amazing run right now, but let's be honest, they are essentially highly advanced probabilistic data compression tools. They operate as these unexplainable black boxes locked into linear statistical associations. And for industrial applications, that simply doesn't cut it. Physical AI demands causal reasoning, extreme high reliability, and critically, the ability to learn from exceedingly rare anomalies in highly complex physical environments. Turing Award winner Joseph Safakis really hit the nail on the head here. He points out that while the web has endless data on everyday topics, out in the real world of industrial engineering, the data points that matter most are actually incredibly scarce. We're talking about catastrophic failures. You might have a decade of perfectly normal operational data, but only 3 or 4 specific failure events. How do you engineer an AI to learn from something that barely ever happens? That is our immediate, pressing hurdle. Which leads perfectly into Section 2, Bridging Data and Physical Reality. So to get around that non-explainable black box problem, we literally have to construct hybrid architectures. We need to take symbolic knowledge, the hard mathematical and physical principles governing our world, and wire that directly into our sensory data. By doing that, we create a real-time mirror world where the digital and physical realms actually converge. It's the only way to get the precise, trustworthy decision-making we need. And that brings us to the Holy Grail, embodied AI. This isn't just a software patch. We are talking about the holistic integration of AI, sensory perception, and actual power electronics, motors, batteries, the works. It's a framework where the system deeply understands physics well enough to autonomously adapt to live environmental feedback. Honestly, this is the critical path toward artificial general intelligence by 2035. Moving on to Section 3, Next-Gen Sensors and Simulation. To actually validate these incredibly complex, heterogeneous systems out in the wild, we need a totally new playbook. We're witnessing a massive shift away from pure rationalism and traditional model-based testing, over to what we call rigorous empiricism. This means relying heavily on advanced multiphysics simulation and real-time cloud rendering. And look, where absolute guarantees fall short, we're compensating by layering in constant, knowledge-based monitoring. But here's the kicker. This whole empirical approach lives or dies on the hardware. We desperately need next-generation sensors. Sensors that can handle macro and micro perspectives simultaneously with huge dynamic range. We need multimodal capacity, processing visual, vibration, and thermal data all at once. For logistics, we're even looking at atomic-level quantum sensing to capture minute environmental shifts in real time. That kind of precision is a total game-changer for reducing damage to high-value goods. Let's look at Section 4, Transforming Factories and Grids, to see what this looks like in practice. Out on the smart factory floor of the future, we are completely done treating machines as just dumb tools. Instead, we're looking at embodied agents that act as true cognitive partners. Using heavy local edge computing, these robotic systems will process multi-sensor data instantly. And backed by continuous training from cloud-based digital twins, they'll be able to pivot from something like heavy welding to intricate precision assembly in a matter of minutes. The efficiency gains we're modeling here are just wild. Driven by these autonomous agents, overall equipment effectiveness is projected to blow past 90%. Meanwhile, product defect rates, they're expected to plummet to under a fraction of a percent. We're talking less than 0.05%. It's the literal transition from mass standardization to flawless mass personalization at scale. At the same time, over in the energy sector, we're essentially going to be managing physical watts using digital tokens. As our power grids take on massive influxes of unpredictable renewable energy, AI and digital twins will step in where human manual expertise just can't scale. We're aiming for a predictive maintenance coverage of 60% across main grid devices, sensing and fixing issues before an outage even happens, optimizing the entire network load dynamically. But there's always a catch, right? To actually run these global physical AI systems, we're going to need an estimated 100,000-fold surge in computing power by 2035. 100,000 times. How do we power that without breaking the grid? By turning our massive data centers into active, flexible energy routers. They won't just drain power, they'll dynamically balance it, cranking up compute tasks when wind and solar are cheap and abundant, and spinning down to return capacity to the grid when it's needed elsewhere. Which makes Section 5 absolutely vital: global standards for AI safety. We are deploying these incredibly powerful systems straight into our most critical infrastructure: the grids, the factories, the supply chains. The systemic risks are just immense. International collaboration and strict global regulatory frameworks aren't just nice to have, they are mandatory. Fighting regulation for a quick, short-term gain is a guaranteed path to catastrophic, long-term damage for the whole industry. Ultimately, safe AI is a universal engineering challenge. We have to build open ecosystems. We need platforms that ensure interoperability and trust across borders. This is exactly why it's being heavily championed right now by UN activities and major global summits. And as engineers, we have got to design with these interoperable safety standards built in from day one. Finally, let's wrap up with Section 6, a symbiotic technological future. The whole point of this massive architectural transition is not to replace humans. That's a huge misconception. The goal is human-AI symbiosis. Just look at this operational breakdown. AI agents become our cognitive partners down at the task execution layer, handling the mind-bending complexity and real-time physical actions. Humans, we elevate. We become the global orchestrators, designing complex workflows inside 3D digital twins and steering the macro strategy. We are currently riding an S-curve paradigm shift. By 2035, AI is going to fully evolve from a digital tool that just processes information into a cognitive, physical entity. It's making the jump from drafting text on a screen to fundamentally reshaping our physical reality, always with the core mission of prioritizing human well-being, safety, and operational excellence. So, we've looked at the roadmap, we know the rigorous hardware requirements, and we see the massive systemic hurdles ahead of us. The ball is in our court now. As the architects literally building this infrastructure, how are you going to engineer your hardware and software today to ensure we get that safe, reliable, and symbiotic ecosystem tomorrow? Something to think about. Thanks for joining me for today's explainer, folks. Let's get back to building.